Okay. So now Ishan will tell us about constraint-based type inference error messages.
Yes. Can I get it to full screen? Huh? F5. Nope. 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 Can't get it to full screen, but that's fine, I guess.
Can you advance the slide? You can advance the slides from there.
Sorry?
Oh, go ahead.
Go ahead. Yeah. Okay. Good afternoon. I'll be talking about getting into the flow towards better type error messages for constraint-based type inference. And I'm Ishan, and my co-authors David and Jonathan are in the audience, and my advisor Lionel is not present here. And I'll start with that. So I mentioned a lot of jargon, but I'll try to explain it as I go on. So firstly, what is a type error? I'm sure a lot of people here are familiar, but I'll just walk through it. Most statically typed programming languages assign types to program expressions, and when that type gets used in a place that expects something else, we get a type error. And this OCaml program has a type error. I encourage you to just eyeball it and see if you can find it. So yeah, so if we give it to the OCaml compiler, it does tell us what's going wrong, and it's saying that there's something wrong at line 9 at the app info expression. It's expecting an expression that has type string star string, but it's getting something that's string star float, and that's it. That's helpful, but can we do better? I think we can. So this is where our work presents data flow style error messages. It presents the same information, but a lot more, and helps the programmer with a lot more context in understanding how things are going wrong. So firstly, the first line is just the same. It says that a float does not match type string. It gives a kind of summary of what's going on, that a float is somehow flowing into a location that's expecting a string. Then it shows where the type float is coming from. It comes from line 4, and the 1.5 in the expression is where the float comes from. And then it flows into the argument to the process function, where we assume a type variable, and then the argument gets applied to the parse version function, and the parse version function expects a string. So this is much more helpful and shows the full context on how we're getting the error. So this is the hypothesis that data flow style error messages are better, and that's what we started with. Our goals for this project were to formalize a practical type system that can identify erroneous data flows, then to categorize these data flows and create helpful error messages from them, and finally to check if those error messages are helpful or not. So just to now we'll try to derive a data flow and intuitively do it, and then see how it's done in the type system. This is again a small program that has something going wrong. Let's see the data flow being derived here. It starts from the 2 and flows into the name binding x. The x is used in the then expression, and the then expression returns the type to the for the if then else expression, the whole thing. But there's also a flow here where the string x flows from the else expression to the if then else expression. We have two data flows here converging at a type variable. The type variable is the type of the if then else expression, and we can see that the data flow also has the sequence of source code locations that we then use to later present a beautiful error message. But where is this data flow coming from? So data flows come from constraints. And here our type system is using algebraic subtyping constraints. And this is the key insight, this is the main insight or the take-home learning from this presentation, is that we can interpret algebraic subtyping as a producer-consumer relationship. You can read this as there's a type A introduced at location or produced at location P0, and it's being consumed at a location P1, which expects a type T. How do we get these constraints? So I'll walk you through one typing rule to show you how we get these constraints. So to walk you through the rule, I need to introduce some notation. We have a location L, which is the program location or the coordinate for an expression, like a line and span for that expression. We have provenances. Provenances are sequences of program locations. There can be 0, 1, or more locations as provenance. We have primitive types like integers, strings, and type variables. And when we annotate those types with provenances, we get a full type. And then we have some typing state. The typing state stores all the relationships, all the data flow or the constraint relationships between types and different type variables. So I'll walk you through the if-then-else typing rule, because that's the example we saw. Now, to type it, we start with some typing state sigma 0. We have some context, and we try to type the if-then-else expression, which has E1, E2, and E3. And firstly, just regularly we type E1 to type T1, E2 to type T2. Notice that the context, notice that the state is flowing through the rules and collecting the constraints. After we've typed the expressions, we introduce the constraint. So we know that the conditional type, the type of the condition must be a Boolean, which means that type T1 is a subtype of Boolean. Here we introduce a constraint. But notice that this terminates the data flow, because T1 flows into Boolean. That's it. It terminates there. On the other hand, the type for the then expression and the type for the else expression flow into the type for the if then else expression, which is a fresh type variable. And that's the type we return for after typing this whole thing. So we see that we introduce two types of constraints. We introduce a lot of constraints here. Some of them terminate, some of them flow into type variables, which can be further constrained. And that's why this is not the complete story, because the actual type system introduces a lot more constraints and type variables. In fact, each name binding introduces a new type variable. Notice that 2 flows into X, and X has we introduce a new type variable A let, which flows into the type variable A then, which flows into the type variable A if then else. And it's the job of the constraint solver to propagate all the locations into a final form which cannot be propagated further. So the 4 constraint thing that you see gets compressed, translated, or canonicalized into the second constraint that you see, which has all the locations for that particular data flow. And from this data flow, we can now create a complete data flow for this expression. Here you see that an integer is flowing into an A or a type variable, and a string is flowing into it as well. Now, if we could leave it here, because languages that support subtyping, like TypeScript, this would be a valid type. But what we want to do is our type system should also support languages that have unification. And that's the second key insight, that we do a second unification pass where we replace the subtyping constraints with equality or unification constraints. And here we find that there's a conflict. The integer is equal to a type variable, which is also equal to a string. And when we see this, we can use all the information we had collected beforehand to present the beautiful error messages that you saw. So just to complete this example, we get a string flowing into an int. We see the highlight, and we see where the string is coming from. We see where does it collide as such, and we can see what it collides with and where it's coming from. This is actually a level 1 data flow. So this is where we do the categorization, and we introduce a category of errors, a category of data flows. You notice that int flows into a type variable and string also flows there, but these are coming from 2 different directions. there is one change in direction. That's why we call it a level 1 error. And on the right-hand side, you can see an error with 2 changes in directions, and we call this a level 2 error. And if you notice, if you think of it carefully, then all unification errors can be represented in this way from level 0 to level n, and it is one measure of the complexity of the error. So this is a tool that we give so that people who are constructing compilers can tune their error messages differently for different complexity of errors. That's how we constructed the error message, but is it useful or is it helpful? To prove that or to find that out, we had to do a user survey, and our user survey was done based on 1 user, 1 system, 10 programs. The programs we selected from a pool of easy, medium, hard that we had categorized, and then they were asked 3 questions. For our survey, we were using 3 systems. Helium is a Haskell compiler, an educational Haskell compiler which gives good error messages for beginners to learn from. OCaml is the standard OCaml compiler, and HMLock is the system we implemented. And the questions we asked them were, did the error message help them understand the error? Did it help them locate the error? What is the problem? Did they understand what the problem is? And finally, after all of that, a free-form question of, what do they think about this whole thing? Well, the quantitative results, we could not show that our error messages were better. In fact, all 3 systems performed comparably well. In this graph, you see that without any significant variation, all systems performed. There was no significant variation across all the systems. And future studies can consider a mix of different problems or different textual error message layouts. More of this is discussed in the paper itself. But the qualitative results were much more insightful, and they gave us a much more positive indication that our error messages are actually helpful. Some of the comments, for example, the green boxes are for our system. So some of them said that it actually helps, and it's much more detailed, and it helps with subtle errors or long or difficult problems. On the other hand, some of them said that, it's not helpful. And on the other hand, some people from OCaml said that they would really like it if they could see where the types are coming from. So it's somewhat conflicting, but still there is a general need for errors that explain where the conflicts are coming from. So what are the recommendations we have from this? That we should support more language features. Our type system supports quite a few features of OCaml, but we can support more. And can we improve the textual representation of error messages? Is there an ideal representation? Can there be an interactive system for debugging, for understanding type errors? And finally, are there other applications for data flows? For example, semantic code search, which is a very interesting problem. Finally, this work is not done in isolation. There are, of course, prior work for this. Although the prior work is more orthogonal to our target, our question of explaining the error, prior work is more focused on error localization or finding a specific expression that's a likely source or the likely fix. And there are two different schools of thought, data-driven techniques or using algorithmic techniques to find that expression. But the most close related work that we had was from Holger Gast in 2005, which introduces a very similar concept of data flows. But our system is like a more practical version of it, proved by the fact that we actually have an implementation, and it also captures complex types like products, functions, and records, and it defines a proper mechanism to report errors and also supports lead polymorphism. So the goals we started with, we did accomplish some of that. A practical type system is implemented and available. We do categorize data flows and create helpful error messages, although that's still in contention. There are more user surveys needed to find out if it's actually helpful or new directions that we can go from here. And finally, that's my talk. Thank you.
Okay.
Hello. It's interesting how if you look at it from a certain perspective, you are doing type inference and checking that the type that you will infer is the type that you find. Can you expand on the connection between your work and type inference?
This is type inference, but we additionally, firstly, we don't eagerly cut the type inference in case a constraint is not satisfied. And secondly, we collect provenance information while we are doing type inference so that we can show how we reached a certain constraint. It is type inference with additional features built in to display better error messages.
So yeah, it's a very nice work and interesting. So not a criticism, but I have a problem that every SE reviewer will have. So regarding a user study, you only consider like one participant. So why not 10 participants?
No, it was one. So we had 120 participants. It was one participant, one system. I think that wasn't clear from my...
So it's not really just one participant?
No. Okay. There were 120 participants.
Yeah, but I think that's a bit misleading because...
Yeah.
Sorry.
I think I phrased it incorrectly. 120 participants were totally actually completed the survey. It was one participant was allotted randomly to a particular system. Okay. That's how it worked.
Yes, so can you say more about, like, you say you include some of the OCaml features, so what kind of features are not considered yet?
So it should support, actually OCaml, it should support most of OCaml features, but more complex features like occurs check or gadgets or type classes, these are things that are not supported. Yeah.
Okay, thank you.
Hi, Apurva from University of Iowa. I think you kind of answered my question. My question was going to be about language features that introduce kind of local assumptions.
Yeah.
It seems that your system may be able to incorporate it. Have you thought about it, or have you just said that it's future work?
Occurs check is something that we can add, and it's like I've thought of it. I can add it in, but adding this for type classes or traits is more difficult. Maybe it's a good question to consider. And any other type?
JDTs or existential types?
That's future work. Again, good question, but we haven't really thought of how to integrate it in. Yeah.
Cool. Thank you.
Okay, so I think my question is slightly related to the previous one. In your presentation, you only showed examples where the path is linear, right? There's one single path from one access to, one usage to one declaration with a few direction shifts. But in case a variable is used more often, you typically get these more tree-shaped like things. Can your system deal with that, or are you planning to expand to that?
So that's a question that I've gotten before. It actually won't form a tree, it will form a layer, and I have that slide in the background here. So just check the slide here. That flow in the example that I shared does not directly flow to the location, to the version argument. It flows into a tuple type, which is applied to process, which gets tree structured. So it can flow through complex constructors, but it won't form trees. It won't form trees, but it can flow through complex constructors. Does that answer my question?
Slightly. So there's a bit of background. What I usually discover is in, type checkers that have type inference. If you don't take precautionary measures, it depends a lot on the order in which equality constraints are solved, where the error eventually ends up, right?
Yes.
And so you need, in case there's a conflict, you need to do some pruning. Can your system support that? Or should we perhaps take this discussion offline?
Yeah, we should, because I don't think I've encountered a situation where that will be needed. So
okay.
I'll allow one last one. You promised to be fast.
So you had 120 participants and you didn't see a significant result. So was it because of high variance, or do you think there's only a small impact?
Can you repeat the question? 120 participants?
Yeah, so if you had 120 participants and didn't see a significant result,
yes,
then either the size of the difference is very small or zero, or the variance was very high. Can you say which you think it was?
There wasn't significant variation in, like, most people seem to find it equally useful, or find it difference in usefulness wasn't
so
too
if
large.
So if there was a difference, it was small. So then the sort of follow-up research question is this as good as it gets? Are we done doing this research? Or is there a lot more to do and we just don't know what to do?
there seems to be, like, the indication here is that there's a lot more to do, because the qualitative results clearly indicate that, and not just the qualitative results, but even during the other discussions with people, clearly these kinds of errors are super helpful. So there's more, like, we do need more research on this, specific textual error message layout, maybe surveys in a different context, maybe live coding. This wasn't live coding, maybe a live coding context. So yes, more directions are there in terms of user surveys or specific layouts.
Okay, thank you.
Okay, so let's thank Ishan again.